他现在听不到我们说话。
哦，
能听到。
能听到吗？哦，他在群里，他在微信里面正说话。
这是吗？
罗教授，你要打开那个静音，你能听到我们说话吗？
我可以听到，我可以听到。It's very good.
哦，那好。Okay. Before you didn't hear us, okay.
你们能看到我的 slide 吗？
能放到那个 slide 那边吗？
把 slide 放大。
对 ，slide 是。
待会儿啊。
上面这个。
它没有共享吧？
不，它共享了，这个是吧？这个是不是就 slide？
我已经共享了。
对。不是。 切换
PPT
切换，现在是人像，我们要切换到这个
切换到
slide。
切换这个 slides， 对，就是这个 PPT。
对，这个放大。
对。
切换那个 PPT 啊。
是他自己的 PPT， 他在共享。
你刚才那点双击就行了，是吧？
对。
你刚才那个，
对，就是
这个双击，这上面蓝的那个双击就行了呀。
对，
是这个，哎对。
嗯，好像不行啊。
罗老师，要不您结束共享，再重新共享一下？
好呀，我们
有点
来一下哎。
可以了吗？
可以了，
可以了，这回可以了。
OK，
这回
是。
现在有多少？好，不管。
不用管了吧？我觉得
没有密码吧？那个是咱们这
有个密码。
有密码，你快告诉人，问我密码。
好嘞，好嘞。
要不再发一次吗？
你发给这群里都没有。
你发过吧？
他只发了个 Zoom 号，没有密码。
有密码。
对，那你赶紧发密码。
我发给你。
对，教室群里不能再发起。
对，在教室群里发一下。我刚才已经发了那个什么了，那个会议了，把密码发一下。谁发？
哎呀，在那个 post 里面那个
post 没放，我有那个 Word 放。post 不太好放密码吧？
那你现在赶紧发一下吧。
对，密码再发一下。
发了。
我把它放教室群里去啊。
对。我发也可以。
我来吧。
如果我们这边想经营的话，是按这个。
现在经营，你现在在经营。Good. Okay. Okay. Professor Law, can we start?
Hey, sure. Okay.
So maybe I would like to spend a few minutes to introduce you to our faculty and students.
Yeah, I appreciate that.
Okay, great. So hello everyone, faculty and students. We are delighted to invite Professor Jianxi Law to give presentations on the topics of toward creative artificial intelligence for engineering design and innovations. So Professor Law is a tenure associate professor of engineering product development and design and artificial intelligence at the Singapore University of Technology and Design, and also a founder and director of the Data Driven Innovation Lab. He holds a PhD from MIT and master's and bachelor degrees from Tsinghua University. He also served as the director of the Singapore University of Technology and Design, Technology Entrepreneurship Programs, and overseas university minor in Design, Innovations, Ventures, and Entrepreneurship. He has been a faculty member at New York University, visiting scholar at Columbia University and University of Cambridge. He has authored over 130 academic publications in the field of engineering design systems and computing, as well as innovation, economics, management, and policies. So his topics today has shown on screens is about design innovations. So what is design innovations and why is it interesting and how is it related to your research? So Professor Law will tell us the story behind his long experience in teaching design innovations. So I would like to turn over the podiums to Professor Law.
Okay, thank you, Prof. Chen, for the intro. Also, thank you and Prof. Gao for the invitation. It's my great pleasure to be here to share with you guys my research and experiences. So currently, I'm a professor at the Singapore University of Technology and Design, SUTD, which was established by Singapore government in collaboration with the MIT, and as an experiment for many of the futuristic ideas for future education and research, which were unable to be implemented at MIT in Cambridge, Massachusetts. And those ideas were had a lot of resistance from the traditional faculty and the existing hierarchy at MIT. So they put ideas in Singapore as an experiment of MIT 2.0 to explore the future of education and research. So the university was founded by Tom McAnally, who was the former MIT Dean of Engineering. And he was actually the dean when I was a student, dean at MIT when I was a student in the School of Engineering. And also Philip Bin, who was the richest person in Singapore at the time when the university was founded, was our founding chairman. And with him and other MIT alumni and a lot of investment and support, SUDD was founded in a very innovative way to transform higher education and research. So the university doesn't have departments or schools. We're structured and organized in 4 design pillars, basically engineering design, system design, information design, and architecture design. And in MIT SUDD International Design Center was established to fuse all the 4 design pillars together through multidisciplinary design research projects. So the center makes 2 calls of research proposals a year for faculties from different pillars to together work on some joint design research project, like a robotic design, architecture design, new material design, devices design, and which require the collaboration across different design fields. So IDC serves as the glue to tie the different design disciplines and fields together. So the center is actually physically located at the center of the campus, not just center of the organization, but also physically at the center of the campus. And you can see the location of the center occupying the first 4 floors of a building street that's right at the center campus. It attracts a lot of traffic, and energy level is always very high, right next to a lot of visitors and events. And IDC has an innovation space on the ground level, and on third level is a IDC Innovation Project Gallery. And we also have a huge research space for students and researchers from different fields to sit together, working on their own research. And what I liked about IDC is the faculty members are seated together across different disciplines. This is the area where I'm seated. Just look at the labels of my office. They're from different domains. So I study data science for design, but I'm sitting together with people studying transport, robotics, wireless communication, aviation. At a traditional university, this is impossible. Most likely you sit together with people doing similar research of yours, but we're unlike that. And as a result, you can see how many PhD students I have supervised from other fields than what I do, right? This is the most exciting part of my SUDD experience, and working with PhD students from many different fields. And that has to, we attribute that to the organizational design, but also the architecture design of the university. Just exciting for me to learn about what the innovators in different fields are doing for my own research, developing innovation tools and methods, but also contributing to the design and innovation of people in other fields. Our undergraduate collaboration is also very, very design centric. The students learn about different subjects by doing design projects, and sometimes they learn about the design process. So in each individual subject, they have to design something using knowledge from the subject. Every turn, they have to design something together in team using all the subject knowledge from 4 courses. And sometimes they also take the third D design project, which requires using knowledge they haven't learned or the knowledge they learned in the past, or they also learn through self-initiated design projects. So students learn a lot of things about design process, but at the same time, by designing, they learn about math, chemistry, biology, and engineering courses better. End of the term, every year you see a large number of design projects from different courses and programs being exhibited in a campus center. Energy level very high, innovation culture is there, you can visually see. So 2018, MIT conducted an internal survey study of emerging leaders in engineering education. for MIT leadership to review the status quo of global engineering education. And SUDD received the largest number of mentions from the thought leaders from different continents about the future, as a future leader of engineering education. SUDD was ranked number 1, and Tsinghua University is number 9. So SUDD's approach is very clear. Focus on design, use design as a lever to integrate different disciplines for education and research in order to nurture technological innovation and entrepreneurship. For myself, after joining SUDD, I founded the Data-Driven Innovation Lab for my own research with a very simple vision. When we design, when we innovate, we are faced with a high degree of uncertainty. We don't know what to design very often, and we don't know how to design, and relying on intuition and serendipity, good luck, is very important for innovation. And the good news are that we're seeing growing data about technologies, innovators, users, and processes. If we can properly mine such data and make sense of such data, we'll be able to make more informed and inspired decisions for innovation. I was very lucky, thanks to the infrastructure of the multidisciplinary research infrastructure at SUDD, I was able to attract students and researchers from many different technical domains, but also social sciences working together to develop data science and artificial intelligence for design innovation. And if you look at our team, it's multidisciplinary clearly, and also multicultural. I'm very happy and fortunate to have this team working together. We mobilize resources and people across 2 campuses at MIT and also SUDD. Also, thanks to the infrastructure being built by SUDD, MIT, IDC. So we have a physical infrastructure for Data-Driven Innovation Lab at 2 locations as well. Myself have traveled across many regions, many cultures, and also many disciplines and domains to study and also to do research. A lot of learning, a lot of experiences I want to share with you later. Despite the multidisciplinary nature of our research, we have been very productive and also lucky to be able to win awards from different academic communities every year. And the awards I want to highlight are those from the International Conference on Engineering Design, the Best Paper Awards twice, and also an ASME Design Theory Methodology Conference Best Paper 2019, and also the SUDD Research Excellence Award in 2018. That is the highest research award for a faculty member at SUDD every year. So the team has developed a number of expert systems for design innovation support. I'll talk about some of those later on. Our research actually is inspired basic research. We start with fundamental challenges in innovation practice. But innovation is a very, our understanding about innovation process actually is very limited. So we have to do some fundamental research to better understand the process in order to use the understanding to develop better tools and methods to support innovation practice. So our research is actually in the posterior quadrant next to the basic research and also applied research. And our work is in the intersection of design science, network science, and data science. And here are some of the typical or common innovators' challenges, especially engineering innovators in practice, right? As engineers, sometimes we develop a new technology. We want to know where we can apply the technology. We believe there are so many opportunities, but we just don't know, right? And prospects are out there, we don't know, and just uncertain. And here's one example. A team of NUS chemical engineer students reached out to me for ideas about applications for their ultra-thin, no-cost, flexible pressure sensor they developed in their lab. They asked me, they wrote an email to meet with me for my ideas about products or potential systems that can use their sensors, right? So they have technologies, they want to explore applications. Another typical innovator's question is, actually started with a design problem. Sometimes in engineering, we have design problems. We want to find innovative solutions. So here is an email from Singapore's Land Transport Authority. They sent an email to SUDD faculty with a bunch of practical problems they face in the highways, in the tunnels in Singapore. They want innovative solutions from SUDD researchers. So they took a social approach, right, to reach out to experts and faculty researchers for ideas. For example, ideas or solutions to prevent water leaking in subway tunnels. how do we find solutions? There must be so many innovative solutions out there. We just don't know, right? Sometimes we don't have a problem. We don't have a specific technology to use. We just want to innovate, right? We have successful products as a company like Apple. Every year we have to add new functions and features, launch new products, right? So we have to keep innovating, otherwise we'll be outcompeted. And that's a common goal for many innovators as well. Singapore's MRT Bureau, the government agency managing MRT, asked us to do an innovation project with them to explore the future functions, features, and structures and layouts of mass rapid transport stations, basically the train stations. And they didn't have specific problem. They didn't have a specific technology to use. They just want to explore what kind of functions and features, materials can be used for innovation. And those are typical innovators' challenging questions. Finding an answer is often intuitive and serendipitous. That was my personal experience as well. When I was doing my master's degree at Tsinghua University, I was very lucky to be part of the 863 project and designing China's first fuel cell bus for the Olympic Games. That was from 2001 to 2004. I was assigned to design a thermal management system for the PEMFC, the fuel cell bus. Right? So I was very, very excited at the time, but how could I design a thermal management system for a fuel cell bus? I started with looking at what Toyota, General Motors, and Mercedes had done for their fuel cell bus. They were leaders in the field. I roughly know what to do, but I was unsatisfied at the time because I feel the work is not enough if I just copy what Toyota has done. I wanted to innovate. I wanted to generate my own ideas for thermal management system for fuel cell vehicles. But as a rookie engineer, I had no idea how to generate my own ideas from scratch. I was very frustrated. One day I got intuition that those researchers or designers designing the space solutions for heat exchangers might have highly efficient designs of heat exchangers in a space because their design conditions are more stringent, right? So I was very strategic. I took a course in a school of aerospace engineering at Tsinghua University. At the time, I already finished all my course requirements in automotive engineering. I just took a course for learning. And Professor Liang Xingang taught thermal fluid system design. He gave a lot of interesting theories, methods, and examples of heat exchanger designs. Some of the examples are from the space programs he participated in at the time. And now we see China space stations up in the sky. Actually, the research had been done for 20 years. One of the things he mentioned that they use beyond the different fields. So basically, when there's a hot fluid, a cold fluid, the temperature will drive the heat dissipation from the hot to the cold fluid. But the distribution of the temperature differences normally is heterogeneous. If we can design the flow channels to make the field temperature difference field more homogeneous, the heat exchange efficiency will be higher. I was so inspired because when I was a student at the Department of Thermal Engineering and Automotive Engineering, I never learned about this. I learned it from the researchers working on space stations. So I leveraged that principle to generate a bunch of concepts for the cooling system of the fuel cell bus. I run CFD, I did CAD models to develop the digital embodiments of my concepts. And I also run simulation and to select the CFD simulation to select the optimal concepts that I generated. I was very excited and happy that I could generate design concept from scratch, but very serendipitous, largely relied on my intuition, my luck of running into Professor Liang Xingang and his sharing of this paper in a course from School of Aerospace Engineering. And later on, I went to MIT for my PhD. I was very lucky to work with a bunch of professors who didn't give me any project. They just asked me to chase my passion. They gave me 2-3 years to explore a research project, which I love. That was great, but also challenging because as a young man, I had no idea to find my research topic. The same challenge I had for my fuel cell vehicle design project. So I took the same strategy. I took many courses from different schools and at MIT. One of the courses was called Network Representation of Complex Systems. The course was just amazing. It was taught by 3 senior professors. 2 of them are members of National Academy of Engineering. At the same time, the course was only attended by 6 PhD students from different departments. And Joe was one of the professors, and each of the professors had to supervise PhD students, 2 students, to do a course project, to do something about network representation of a complex system you choose. So Joe was a pioneer of AI research. He was a student of Minsky in the 1950s, and he developed a system when he was a PhD student. The system was the predecessor of MATLAB today, 50 years ahead. And later on, he became the director of CSAIL, the Computer Science and AI Lab at MIT, Dean of Engineering, and the provost of MIT. When he was teaching us, he just stepped down from the provost of MIT, the post. So what surprised me was, as a mathematician by training or AI researcher, he was actually talking about organizational structures in different cultures instead of a math, instead of a computer science. And he was basically talking about how Issa Reilly's army, Issa Reilly soldiers communicate in a flat structure in Japanese army. The organizational structure is a tree. In the US Army, you have the tree, but you also have landscaping communications. So at the time he referred to a concept called hierarchy. His point is that in Israel, hierarchy is basically long hierarchical structure. In Japan, it's very hierarchical. US, kind of in the middle, it's a mix. So that was very attractive to me because as a Chinese guy, hierarchy is hard-coded in my brain. When I approach a problem, I start with thinking in a hierarchy. So I approached him to develop a measurement or quantitative metric to detect the hierarchy embedded in different complex systems. At the time we started, he was also interested because he was just talking about it instead of working on it. So I proposed to work on it with him. So we were talking about food webs where the hierarchies in food webs were energy flow, hierarchy in software core graphs were information flow, and hierarchy in transportation networks were materials flow. We're trying to get some inspiration across different domains in order to come up with a metric measuring hierarchy of different complex systems. One day, the inspiration for me came again from my prior field, which is fluid mechanics. I did a lot of projects analyzing the flow field around cars. When I look at those simulated flow fields, I hate the turbulence. I hate the swirl, the vertex. I like the laminar flow because the swirls, the turbulence mean energy loss. We want to minimize that when we design artifact in the flows. As an undergrad student in fluid mechanics, you should have already learned about laminar flows, which is linear unidirectional flow, and also turbulent flow. That means the flow elements goes back and forth, right? The energy loss is there. So with that inspiration, I came up with a flow hierarchy metric, which basically measures the portion of dependencies in a complex system which are not part of a cycle. So in this case, on the left-hand side, it's like a Japanese army, right? Unidirectional, there's no cycle. So hierarchy degree is 1. On the right-hand side, this is like Issa Reilly's army, and every element is in a cycle and information synchronized. There's no hierarchy, it's a fair game. In the middle, 5/7 of the links are not part of cycle, but 2 links lost direction, they become symmetrical. So hierarchy degree is 5/7. So I presented to Joe, he was very excited. He found this metric very lovable and creative, and he supported me for my qualified exam. He commented on my capability as being creative to my committee. My professors told me later on about that. I was also very surprised he said so because I never thought I'm a creative guy. And especially what I did with him was very naive from the perspective of an undergrad student in fluid mechanics. But he is a pioneer leader in AI. He found my work as very creative. So I was very surprised. Then I reflected for many years. I realized a shortcut for creativity, which is to draw analogy across domains. If we can leverage some of the existing materials, structures, algorithms, and methods from one domain and to solving problems in other domains, we easily get novelty because those things in the source domain might be boring, common, low novelty, but they appear to be very lovable for the problems for the people experts in the target domain. So there are many other analogical design examples. For example, China's national stadium is called Bird's Nest because the design inspiration is from nature, Bird's Nest. Artificial neural network is called artificial neural network because its inspiration is from the biological neural network. Red packets, right? In WeChat, Weixin Hongbao is called a red packet because the inspiration is from the physical red packet. We don't call it money transfer. We call it red packet because the inspiration is by analogy. However, because of my immersion in the engineering design course of the SUDD, I've supervised hundreds of design projects at SUDD. All courses require design. So the students work with me to generate ideas for prototyping for their design projects. So I learned about how they generate ideas. I become very empathetic about how young people generate ideas for their design projects. What I learned is not so many of them are very good at analogical reasoning, but many of them are very good at combining, recombining technologies and devices and stuff to create new stuff, to create new designs. Bubble, milk, and tea combined together, new product, bubble tea, right? There's no analogy, but just combination. Karaoke and shower. Right? When we take a shower, we sing. Let's put karaoke there. It's an invention. There's no analogy, but just combination. And Jewel is a wonderful space place in Singapore, which is next within the airport. The design actually synthesize the shopping mall experience, a park, and airport. The three combined in one leads to this innovation called the Jewel. Just exciting. Flying car is a combination of a car and airplane. Terrafugia is recently acquired by Geely, the Chinese company, for $4 billion. When I was a student, this company was built actually by a few students at MIT from the mechanical engineering and aerospace engineering department. They came together to generate this idea of a flying car based upon their combined expertise. LiDAR, AI, and the camera together combined with a traditional car, we get a driverless car, just combination. iPhone 8 plus wireless charging and Face ID, we get a new product called iPhone X. Companies like Apple just recombine new technologies with their prior ones to generate new products. There's no myth, just combination, analogy, or other ways of creative transformation, which allowed us to generate new knowledge and concept. Nothing is a scrunch. The ideation process, as we understand from the design creativity literature, is just a transformation of what already have in the knowledge space. From my observations in design innovation workshops, supervising students, I learned combination is most widely popularly used creativity operator and analogy. A creativity operator is a term that came up with my co-author Victor Tan to describe the cognitive process we use to generate creative concepts. So we call such stuff like analogy, combination, creativity operators. So combination is the most popular, analogy is the second, but at the same time, there are also other creativity operators in the brain. For example, elimination, substitution, and reverse thinking. So here's my simple model of creative ideation. When we generate idea, we're just transforming existing ideas using our creativity operators. By leveraging the mathematical terms, operators, operands, what we do is to apply different creativity operators on existing knowledge operands, so we generate new ideas. That's my mathematical view of the creative ideation process in a human brain. So the question is, where do we find the knowledge operands to draw knowledge, to combine and transform, right? So for example, companies often ask this question. Yes, we know we need to combine new technologies with existing ones, but which new technologies? Right, companies continually ask me to give them ideas about new technologies to combine with their products. Here's just one example with the Chang'an Automobile R&D Center. So very often, like Chang'an Automobiles, many companies and designers, they know their limitations. They only know limited domains of knowledge, like cars or phones. They want to learn from other fields and learn from other experts. So we go out to ask experts for ideas, for inspiration. Sometimes we brainstorm, want to be inspired by the peers. Sometimes we go on the internet and look into existing exciting design repositories for ideas. Sometimes we just use Google Scholar or Google Patents, read them, and for inspiration. But the challenge is that the creativity operators, analogy, combination, or social approaches, reaching out to experts or brainstorming, they're limited by the people you run into. Everyone is limited in our memory and knowledge. The data-driven approach can lead you to unlimited inspiration, but the search process is serendipitous as well. Very often, you get fixated on a paper or a patent for a week, for a month. It's very easy for you to get fixated and kind of get beyond that. So what we need is a global and rapid search for inspirational stimuli. And when we travel to a new place, we already have a technology for us to rapidly search for ideas about what to visit, which places to visit, what attractions we should experience. Let's say, assuming you are in this place and you have 5 hours of time, you want to explore the space. What can you do is to use your Google Maps to locate where you are, and you explore the Starbucks, the shopping mall, and interesting places in the neighborhoods to spend the next hour or two, right? Or you explore alternative, the system will recommend alternative passes, routes for you to travel from where you are to where you want to go, right? So the magic of a Google Map is it provides information about the distance between where you are or where you can possibly go, right? So you're more informed about what you can do when you travel. So when we innovate, when we design, we're also traveling in the knowledge space, and we have our spot for our problem, for our specialization, for our interest, for our technology. There are so many interesting possible inspiration, useful technologies out there, but they're just too far away in the knowledge space. We cannot sense them. We're not aware of them. And once we're aware of some of them, we also find it very hard to learn about them because the knowledge distance is very far, right? And most of the time, we can only think of the stuff in the neighborhoods of what we know. So the story basically tells knowledge distance between our knowledge and the potential sources of inspiration conditions the analogy and the combination across different knowledge rooms. So the key variable here is knowledge distance. That's actually my core research about. So knowledge distance has been built upon a number of wisdom ideas that the smartest people in the world have already proposed. Patrick Winston is a pioneer in AI, MIT professor. He died 2 years ago. That was very sad. So in his doctoral dissertation about 50 years ago, he already said, it's only possible for us to learn something that we nearly already know. Learning cannot be jumping. We cannot jump. Right? We cannot cross very distant domains. That's the idea here. And Art Markman is a famous cognitive psychologist, and he's actually one of my research collaborators for a research project. And Art's most important contribution is analogical reasoning. He argues that knowledge is organized in categories. When we learn, we make inferences across categories. The more similar categories will allow analogy to be joined easily, and analogical reasoning will be easier, so the inference will be easier, so learning will be easier. So the idea is when we learn or innovate, we actually, most effectively, we draw analogy across domains enabled by the similarity of different categories. So our team actually spent a few years to quantify this concept called knowledge distance using pattern data, which actually have natural categories of different technological knowledges there. So what we did was to experiment different metrics using different information items from pattern data to quantify the knowledge distance between different technology categories. So we found out the optimal measure of knowledge distance. We use to create this network map of the technology domains. Here in this map, different bubbles are different technology fields. They're positioned according to knowledge distance as we quantified. And so this technology's network map fulfills the idea that the technology space is a nearly decomposable complex system. So we decompose technology knowledge space into different domains so we can most effectively learn and innovate within domains. But when we need to innovate, more radical innovation requires crossing domain analogy and a combination for innovation. So if you roam in this map, you see finer grained technology fields, just like how we use Google Map and Baidu Map, you roam in, roam out to see information at different levels. So with this technology space network, we actually construct a connected vector space. This vector space model will allow us to position a specific technology in a space, making inferences from it to other white space, and also relate different technologies in the vector space. And also do the same for a city, for a company, or for a person. We also did some design science research to understand the implication of knowledge distance for different kind of innovation behaviors. By analyzing 2 million of inventors' digital footprints, we found that inventors are much more likely to invent technologies in proximate domains to their prior inventions. But the inventors are more productive in more proximate domains, but they're less likely to hit breakthroughs. So you can be very productive in proximate domains, but very unlikely you can have a breakthrough innovation. But innovators do not often diversify into other fields. Sometimes we just stay where we are, but we draw inspiration from other fields. So we did this human experiment with the Engineering Design Innovation course at SUDD. In this course, students are expected to learn about engineering design innovation process. They do so by designing something. In that year, students were asked to design spherical rolling robots. So they were asked to generate ideas, prototype, and exhibit designs using this prototype platform technology we give to them, which is a spherical rolling robot. The students had to generate ideas about what to prototype in Wake tool. So those are the final products coming out of the course. Some of those rolling robots can swim, some of them can fly, some of them can fight. A lot of creative designs, but in Wake tool, the students were struggling to generate the concepts to prototype. Right, so we asked them to search for inspiration from the patent database, from YouTube, from any sources on the internet. We also asked them to report the inspiration source. So which patent provided inspiration, which YouTube video provided inspiration, how the inspiration allowed you to come up with this specific concept. So with that data set, we were able to position the inspiration and also position the design problem in the total technology space, then calculate the knowledge distance. Then we found the patents nearer to home are used more often for innovation, and more novel concepts actually use more distant stimuli, and higher quality concepts use more proximate stimuli. So these two projects are research experiments are actually design science research, aiming to understand how knowledge distance can enable or condition innovators' behaviors for drawing inspiration across domains or diversification across domains. So based on the understanding, we did some design engineering research to develop this expert system called InnoGPS to precision specific technologies, explore the neighborhoods for combination or analogy, and also suggesting passes of the technology for you to learn for innovation in far fields. So the design inspiration again is by analogy, because I'm myself is an analogical thinker. So when I designed InnoGPS, my inspiration was from Google Map. So we use Google Map to position ourselves and explore neighborhoods and directions for far fields in the physical space. In InnoGPS, we position technologies, explore neighborhoods and directions to far fields in a technology space, not the physical space. Let me give you two examples of using InnoGPS for innovation. So here's the question, the problem from LTA that put forward at the beginning. Water seepage in the subway tunnels. What kind of innovative solution we can get? This is a practical design problem. So with InnoGPS, we first position the problem, water seepage, in a total technology knowledge space. So the red bubbles highlight the domains where existing solutions to water seepage have already been generated. And LTA's specialized domain is road, railway, bridge construction domain. That's the target domain. What we need is to find a solution from the red bubbles as the source domain of inspiration. So let's go into this very close near field called layer product. We can find this multi-layer composite concrete structure for water leaking prevention. Wonderful. Why don't we just put this multi-layer composite concrete structure to fabricate the wall for the tunnel to prevent water leaking? Let's go further down in the space, organic material applications. Wow, so these guys have invented natural materials, composition or mix of the natural materials with a specific composition to prevent water leaking from ponds and reservoirs to the soil. Hey, we can use that composition and to fabricate the wall to prevent water leaking from the soil to the tunnel, right? This was a technology developed for NASA, actually. So medical and hygiene sounds like a totally unrelated domain to tunnels, right? But by looking at this invention in medical and hygiene, which is a appendage protection structure, I quickly generate idea of fabricating a temporary cover to cover the leaking point for temporary fix of water leaking in tunnels. So machine elements is even further domain, right? So, but we still find the inspiration from that domain. Reinforced hose using textile to prevent water leaking from the hose. Wow, actually we can use textile, put the textile layer here in the tunnel wall to prevent water leaking. So in just a couple of minutes, we generate a number of ideas to solve this practical design problem of LTA. Sometimes we don't have a problem, we just have a product, we don't want to innovate around the product. What can we do with InnoGPS? right? So assuming that we're designing a rolling toy, we had a successful product rolling toy, we want to innovate opening. What we can do is to position rolling toy in a space, explore the neighborhoods and the far fields, identify potential inspiration from the far fields in the white space where those concepts have never been used in rolling toy designs. So for example, once we enter this domain called check-in devices, I discovered some interesting concepts like display and gaming. Let's just combine that with a rolling toy for a new product. Monitoring, hey, let's add a camera to monitor a surrounding and build remotely using a rolling toy. And authentication, wow, yes, we can embed RFID chip in a rolling toy to turn it into an ID, authentication device. Data collection, wow, yes, why don't we put some ambient sensors in the rolling toy and throw the toy in the pipes or dangerous environment to monitor, to collect data about the environment. Okay, so I generate those ideas in 1 or 2 minutes by just looking at the design concepts from check-in device domain, which is in the white space of a rolling toy. Just combine them with the rolling toy, we generate new ideas. And we can also randomly explore neighborhoods in the total space. Inspiration can come from anywhere. From the lighting domain, I discovered a concept called LED, LED. So why don't we put LEDs in a rolling toy, right? Then we can design mobile lights. Here's one of our student designs, putting LEDs in a rolling toy. So to provide mobile lights in a public space or at home. So the inspiration actually can come from different domains. It can be far or close to your home design domain. But we just need to be aware of the implications about the knowledge distance between the inspiration and the design problem. So we actually had this function, GPS, to rank ideas by knowledge distance between inspiration and the design problem. If you really want to go into far fields, GPS will also prescribe the pathways of learning from where you are to the far fields. And GPS is the most useful for people who have no ideas, the people who are not creative. For creative people, it's also useful. Bob Langer is an MIT professor with more than 1,000 international patents. He has a lot of ideas. He spun off about 50 companies already from his lab. So when he was visiting us, I asked the question, Bob, you're an expert of polymer science and drug delivery. What kind of innovation are you thinking about for your next stage of your career? Then he mentioned cosmetic products. I'm thinking about cosmetic products, nutrition, additive manufacturing. Wow, great. So I went home to position him in a total knowledge space. I also positioned additive manufacturing and also cosmetics. Then I found Bob is very close to cosmetics, but very far from additive manufacturing. That means it's easy for him to develop cosmetic products, but difficult to do additive manufacturing, and nutrition is in the middle. About 2 months later, one of my students told me, wow, Bob's lab already spun off a company and sold the company to Shiseido. So basically, Bob made the rational move to the neighborhoods. Sometimes you make the move not in a long rational way. You just chase your passion. Larry Page, Google co-founder, right? He started Google, was very successful. He was a computer scientist, but he had this childhood dream to design autonomous vehicle, okay? A vehicle is very far from computing. No problem. GPS will prescribe the shortest path of learning or capability building for you from computing to car. Actually, Google followed our prescribed path for learning and capability building to travel from computing to vehicles over the years. So GPS basically guides the cross-domain inferences of design knowledge and concepts by knowledge distance to stimulate analogical reasoning and combination of creativity, and also inform innovation decisions and planning. The system has been trial used by a number of organizations, companies, and also individual users. I'm most excited about the use of GPS in a number of engineering design courses at SUDD. Students are using GPS to generate ideas to prototype for their design course projects at SUDD. We have published a number of papers about the theoretical methodological foundations and also applications of GPS. GPS is actually a computer-aided ideation for concept generation at the fuzzy front end of the innovation process. It's very different from what I did 20 years ago at the Tsinghua University. At the time, I used American software to do CAD and CAE to simulate the flow field around cars. That's in a later stage of design process. After you already have the concept, you can create the CAD model and simulate, analyze it. But at fuzzy front end, we don't have a software. And InnoGPS is one of the pioneer software for concept generation around the world. 20 years ago, I was using American software for my CAD work. Today, I'm creating a software for, say, AI, for people like me 20 years ago to generate engineering design concepts. So my experiences of observing the uses of our students and engineers using InnoGPS, I found the effectiveness is affected by the user's creativity, the user's creative thinking skills, and the user's knowledge. So that needs to, it's conditioned and limited. So I realized it's important to let computers ideate and generate ideas. That requires the computerization of the creativity operators from the human brain to the computers, and also systemize the artificial knowledge memory. So we need artificial mind and also artificial memory in order to have full computer ideation. That's the InnoBrain project I'm working on with Art Markman, a psychologist. So the InnoBrain we're building has artificial memory, and the InnoBrain will learn from the users, the human being, for design problems or any stimulation, and make inferences in artificial memory, and also combine the inferred knowledge together with the stimuli to generate new design concepts. We have done a lot of work to develop the artificial memory on top of our technology network. We're also training new network classifiers to be able to processing any unstructured multimodal data about technologies into our artificial memory, not just patent data, but also papers, articles, or the kind of conversations we have today. And a lot of work about deep representational learning for technical documents. We also created a technology semantic network of 4 million engineering terms as a bottom layer of the memory. So we call this TechNet. Our TechNet actually outperforms Google and ConceptNet and WordNet for engineering design knowledge representation, and also engineering technical inferences from technical concepts to technical concepts. And we use it for a project to generate design ideas for future flying cars. This paper is published with Artificial Intelligence for Engineering Design, Analysis, and Manufacturing. We're also upgrading TechNet to include qualitative information relational information between different technical concepts. So the artificial network memory we built is hierarchical, having categories in the middle, semantic at the bottom, and networks in the middle, and also at the bottom, to categorize, to store knowledge in different categories, and also guide inferences across different categories by knowledge distance. So the challenging part is to develop the artificial mind, which is a computerized creativity operators. We have created a number of design description sentence templates to implement analogy, analogical thinking, and combinational thinking. And we're also, but those are very structured templates we generated. We're also exploring OpenAI's GPT-3 transformer based upon common sense knowledge data, and trying to combine them to have natural language generation capability for InnoBrain. So the InnoBrain will present its ideas in the natural language format that human engineers can understand eventually. So once the ideas are generated by computers, we need to evaluate them. Our team has done a lot of work about concept evaluation using machine learning. And so this is easy because of optimization problem. What we haven't done is human AI interaction. Right? So once InnoBrain has ideas, eventually it needs to be used. Novelty, usefulness are subjective. The users, we have to put users or designers in a loop for design and innovation. So we haven't done it, but I sent my former PhD student to a group at the Carnegie Mellon University, which is specializing in human AI interaction. Hopefully we can collaborate in the future and maybe have the student come back to join our group again to close the loop for artificial creativity with InnoBrain. That's about my research about creative AI for engineering design innovation. We're still making progresses, not there yet, but very exciting, very exciting. So I actually also put some slides together about this emerging field about design engineering because Prof. Gao was very interested. I wonder if you want me to go through those slides very quickly, or you want me to take questions about my research?
Professor Law,
yes.
You have 10 more minutes for the question. Do you want to save the time for the questions, maybe?
Okay, let me go through the slides for maybe 2-3 minutes very quickly. Then we take some questions. Is that okay?
Yeah.
So this is not very related to my research, but maybe very interesting to you. So outside China, there's a new field called engineering design that's emerging. Design, so this is based on the fundamental perspective that design actually distinguishes engineering from applied science. Design distinguishes engineers from technicians. Engineers actually design. Engineers are designers using physical knowledge, using scientific knowledge. So engineering design or design engineering discipline develops formal structured design series, methods and tools to support the process of designing, creating new artifacts, new and useful artifacts with technical and scientific knowledge. In addition to SUDD, MIT, Cambridge University has a long-standing engineering design center that has trained many PhDs, developed a number of design methods and tools. And those PhD students in the 90s became faculty members. They're very active in today's design engineering field. Imperial College London launched the full stack design engineering school. James Dyson donated 12 million pounds to kickstart this design engineering school with undergrad, grad, and also PhD education and research. And TU Delft has a design engineering school, but it's more toward industrial design. And in China, I recently discovered SUSTAC launched a new school of system design and intelligent manufacturing. That's the only engineering department or school in China that put design in the name. When I looked into their curriculum or their vision statement, I got confused. It's quite messy. It's unclear what they intend to do. Probably they just put some sexy keywords together and to develop 新工科, whatever, I don't know, right? And so it's unclear what they intend to do, but they're trying to experiment new engineering disciplines. And so internationally in Europe, we have Design Society as an academic community for engineering design research and education. In the US, it's a ASME Design Engineering Division that I used to go to. Leading conferences are ISAT, International Conference on Engineering Design, and also IDTC, International Design Engineering Conference in the US. My team has been winning best paper awards from those conferences and societies. What I found very interesting at those conferences is I don't see Chinese people. I actually don't find any Chinese faces when I go to the design engineering conferences. When I go to the operations research conference or mechanical engineering conference, I see most of the attendants are Chinese or Indian, but at the design engineering conference, I don't see Chinese, largely because in China, we don't have this discipline called design engineering or engineering design. We don't educate people in this domain. We also don't do research in this domain. So those are the active engineering design scholars behind the societies. And also driving those universities. They're also my collaborators, my friends, and also my mentors, some of them. And those are the leading journals: Design Science, which is quite new, Research Engineering Design, AI EDAN, and JMD and JED. And I'm actually associate editor for two of those journals. I'm also on editorial board of Research in Engineering Design. Actually, most of my papers are published on JMD. So I'm very active in those academic communities. I just want to share with you, we're launching a new special issue called Natural Language Processing for Design with Design Science. I'm going to work with John Piero for this special issue. Recently, we added a special issue called Innovation in Design Process. And that was invited by IEEE Transactions on Engineering Management. Very interesting. After we finished the special issue, the editor-in-chief invited me to become a department editor to continue promoting design in the engineering management community. I'm also promoting design in technology innovation management community, playing my role as the evangelizer of design research. There have been a number of established design method textbooks for undergrad students in engineering design, and also a number of design theory books to draw foundations from. Those are the classic and some typical research topics about design theories and methodologies. And the yellow ones are what I'm working on. I found most of the engineering design researchers are traditional engineers by training, but they're also very interested in creativity and innovation and draw foundations from cognitive science. And increasingly, AI and the data science are being used in the design process, and that opens up many research and education opportunities. At SUDD, we launched a new degree program called Design Artificial Intelligence, which basically promotes the use of artificial intelligence as a tool for designing, for discovering user needs, generating concepts, evaluating designs, and the communication designs. So AI is recognized as a tool for design process. And I'm also involved in this program. So here's my proposal for Tsinghua Shenzhen. You don't have to pick it. But when I was creating the slides, I generated this idea. So we can potentially create the Institute of Design Engineering as a second dimension unit to tie the existing traditional engineering institute together. So we can have a small number of core faculty working on design engineering. There are professors in design engineering to develop a series, methods, and tools for design engineering. But at the same time, we can have a large number of professors from the existing pillars, existing institutes, like material science, environmental engineering. If they also supervise PhD students from the Institute of Design Engineering, they can get a second title. They can hold a dual appointment called design engineering. That will be able to fuse those different units together by designing, by doing design research, by co-supervising students, and tying those institutes together. And for design and innovation, it will be exciting. Okay, so here's the mission statement of Tyson School of Design Engineering at Imperial College. I found something very interesting. In addition to design thinking and engineering, they also emphasizes the innovation and enterprising. MIT IDC, in addition to developing methods, tools for design, they also emphasizes design science and also entrepreneurship, right? This is exciting because and we realize that design has a strong interface with entrepreneurship, actually. So this is how Elon Musk defines himself as a design engineer, actually.
An entrepreneur. But people that know you say.
I would say.
So Elon Musk doesn't like people to think he's a businessman.
No?
No.
What are you?
I'm sure there's probably lots of analysts on Wall Street who agree that I'm not a businessman.
Okay, well, what do you think you are?
I'm an engineer.
An engineer?
Yeah. I like engineering and design.
Okay, that's exciting, right? Elon Musk defines himself as an engineer, and what he does is engineering design. Actually, engineering design is the core activity in the innovation process to connect scientific research with entrepreneurship. Without designing, entrepreneurship is up in the air. There's nothing to commercialize. There's no product. You have to design, right, before you can push the product to the marketplace, to users. Also, designers need knowledge, need fundamental understandings to be able to design. So design actually closes the gap between scientific research and entrepreneurship in the United Innovation Process, which is a paradigm I published in 2015 as the first ever peer-reviewed article in design science. So design is the core action of the innovation process. That's my view. If you look at my InnoGPS project, actually, I started with design science research to understand how knowledge distance affects creativity. Then I used the understanding to invent InnoGPS. Now we spin off a company to commercialize InnoGPS and hope InnoGPS can be used by a lot of people and become a real innovation, right? So myself published this paper, innovation in design science on United Innovation Process in 2015, and I also implemented in my own research practice. So this has been working very well. By taking this strategy, the Data-Driven Innovation Lab has been able to contribute to a number of fields, but at the same time with design science and engineering as the center of gravity. That's it, thank you. Hope it's useful. Hello? 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 All right, what happened? Hello? Hello. I cannot hear you. Can you hear me? Hello.哎，高老师，我听不见你们了，不知道怎么回事。
我们都听见你啊！
啊，哎呀，我听不见。
我们都听见你。现在我这手机也打开了。
怎么回事啊？怎么我听不见你们？
我是微信，
现在能听见我吗？
能听见你啊！我们一直能听见你啊！
但是我为什么听不见你们？很奇怪。
哎，这解除静音啊，
这样。
是我们这边的问题，我们这边的 technical 的。
把静音解除啊！现在是静音了，现在。现在能听见吗？
我还是听不见你们。
能听见吗？现在？
听不见，只有微信，电脑听不见。
电脑听不见啊。
这样能不能就是
其他的那个线上的老师
可以
听见吗？
听不见。如果有问题的话，可不可以放到那个 chat box 里面，然后我或者通过微信告诉我来这样回答也可以，或者在 chat box 里面。然后如果你们能够听见的话，因为你们可以听见我，对不对？你们可以听见我就没有问题。
我们能听见你。
你们能听见我的话，
你的就是顺的麦，你打开的话，应该大家可以听到。
对，完了问大家有问题没？他回答都能听见的。
对，如果你们把那个问题放在那个 chat box 里面，我就根据那个来回答，或者通过
大家可以在其他老师能听见吗？可以在那个问题框里头提问题。
刚才我讲的这个 design engineering 这个 field， 高老师，你们那边有听见吗？有听见是吧？
我们都听见了。你说话我们始终能听见。
哦，奇怪。
对，就是我们说话你听不见啊。你刚讲的话。
网络不稳定。
喂，罗老师，你要不要打开你的麦，然后你可以问一下那个线上的同学老师他们有没有问题？
哦，那个
因为我现在没办法问他们。
OK， 好，那各位老师，如果大家有问题的话，可以在那个 chat box 里面，敲在那个 chat box 里面，这样因为because I cannot hear you guys, so if you have a question, you can put your question in the chat box. I'll look at those questions and answer verbally. Yeah.
现在那边听不见了，是不是？
其他老师听不见，看看方可从这台电脑进行一下。然后就直接从这。
稍后啊，稍后，我们用另
外一台电脑试试。
Hello，
哎，可以了，
可以吗？
可以了。
OK。
但是我们这边讲话能听到吗？
现在好了。
罗老师能看到高老师吗？
能看到我们吗？能听见我们吗？
哎，可以看得到。
那把这关了，要不然。对，用这个来，用这个。
对。
你问吧。
Okay, hello, everyone. Can you guys hear us? 如果把这个关掉以后，就不会有回音很小啊。
对，你把那个静音关掉，同时要把它的声音外放给关掉。
对，把那个麦克那个 speaker 也关掉。Okay, so we can now start to enter into our question Q&A sections. If you have any questions, feel free to ask here.
No question. So I did a good job.
Hi, Victor. Can I ask a question?
Hi, Faisal. Yes.
Hi, Professor Liu. Thanks for a nice presentation. My question is, and like you also give a very good example from Elon Musk, design is an integral component of engineering. So when we teach, of course, design is one of the main component of any teaching related to engineering disciplines. So how does this approach of SUTD differs from conventional engineering? Of course, like you mentioned, there will be more emphasis on innovation, but how does it affect then other aspects of the engineering teaching?
Okay, that's
like,
actually
let me for example emphasize. So let's say data science can be helpful in many disciplines. So I can also argue that bringing data sciences into engineering courses can be helpful for those courses, right? So this, but yes. Then this may have this, but this may also have an effect on the other, other aspects of that specific program. So how can we somehow have a good balance by bringing more innovation and design into a conventional engineering programs, which already have an integral design component?
Okay, that's a very good question. Actually, engineers design, right? We all design. If we don't design, we're just technicians, or we're just assembly line workers, because we don't use our creativity to do something. So engineers, by definition, design. But in traditional engineering education, and we just design it. We learn about what has been designed. We learn about the physics behind the artifacts. For example, I studied thermal engineering, where I learned about turbo machineries. Later on, I started automotive engineering, where I learned about combustion engines. But I never learned about the formal process, the theory, which would allow me to create the next generation of energy devices. Right, so I just learned what other people have already created.
Yeah, like if we teach a course and we teach them design methodologies, the students should be able to, if they are given a problem which differs from what exists earlier, the students should have developed the capability to learn their concepts, to try to find a solution of some problems, those solutions which do not even exist before, right? It's not like they're designing something which already exists. If they learn the course well, they should also have the capacity to try to find out.
Actually, that's exactly what we do here at SUTD. I don't know if you can see the screen. Actually, I have some hidden slides here. So at the SUTD, all our courses actually have a design project. When students learn about physics, we have a design project. When students learn about physics and math together, we have a design project for them to combine physics and math together. We also have a systematic engineering design innovation course, like what you said. Just allow students to experience the design process to design something for innovation, right? And actually, we have a very comprehensive approach in terms of a space design, curriculum design, teaching team design. And in order to make mathematics course also a design course, students learn about mathematics better by designing. And also, we also have this kind of so introduction design is the first year design course. I co-taught with this guy. This guy is an architect. Look at these students are designing different things based upon their own ideas in team, right? And mathematics design courses, and also every year, every semester, end of semester, all the courses will put student design projects in a campus center and to learn from each other, to inspire each other, to generate an innovation culture in a community, right? Those are just some of the design projects that are supervised with this, my friend Canadian guy, architect, and exciting. So what I learned here is, in addition to structured design theory methodologies, it's also important to have to use such approach like design project, experiential learning to nurture innovative culture and also tighten up the community of people from different disciplines. Certainly you can design with a bunch of people in your lab, but it would be greater that you know many people in the community and you don't have this cognitive barrier about them. So you feel very comfortable to work with people from architecture, from material science, from computer science to work together to entrepreneurial design. Here's another course I teach at SUDD, which is entrepreneurship, traditionally defined. This is a business course. If you go to any other university, entrepreneurship is a business subject. But at SUDD, it's an engineering design course. So students work in team in my entrepreneurship class to identify problems, to ideate in teams, to build a team, design a team, to prototype and market and launch the products on Kickstarter and sell it on internet and also on the ground and pitch to investors. They basically experience the entire design innovation chain. They're not just prototyping, designing, generating ideas. They're actually experiencing the innovation value chain. Actually, as part of the course, we also send students to Shenzhen because for hardware projects, manufacturing and product realization is fundamentally important. So we actually have a number of partners in Shenzhen, like a production realization companies, manufacturing companies that used to work with the startups, and also this American accelerator program, HAX, which is located in Huaqiangbei. Our students go there to pitch our projects to the American entrepreneurs every year. And just exciting. Anyhow, so here's the collection of the startups, the technical startups coming out of our entrepreneurship class. So the approach actually is more systematic than just teaching the students design theories, design methodology, and ask them to design something. So what's I found from my experience, I learned what's also very important is to build ecosystem of stakeholders in the innovation value chain to work together for research and education across different disciplines, and also nurture a culture of innovation by working together through design.
Okay. Yeah, thank you.
That's a fundamental, very important question. Thank you.
Hello, Professor Luo. Hi.
Oh yes.
Hi. My name is Funko, and we are also here working on the cross courses here in Tsinghua and Shenzhen. And I like very much what you say. You use design as a fusion for different disciplines in your IDC. My question is, what do you think is the biggest challenges? Because from my experience, it's actually not easy when you're trying to bring people from different backgrounds together and trying to do something.
Yeah. That's a wonderful question. So one thing I learned from this practice is we can use money to tie people together, right? So IDC actually, we can use research funding, and we design a research scheme. We use research funding to encourage people to work together. For example, all the IDC projects, if you want to get $500,000 funding for an IDC project, you have to collaborate with someone. Your co-PI or PI must be from another pillar. So we have 4 design pillars, right? Engineering design, system design, information. You have to work with, for me in engineering design, I have to work with an architect or information scientist or computer scientist or system engineers to have a proposal that's matched for funding from IDC. Okay, it's top-down design. Yeah, it's top-down design. Another idea is to require co-teaching. For example, this course, Introduction to Design, for design courses, it's required to have faculty members from different pillars to co-teach one cohort class. So this module has 8 different classes. For each classroom, we have at least 2 or 3 faculty members from different fields. So for this year, I had an architect. For another year, I had an architect and also a robot designer, robotics person. So that was exciting, not just for students.
Sorry. But what do you think is the incentive for the faculty themselves to collaborate on such a course?
Okay, so that's also a very important question. So there are different kinds of faculty. There are faculty members like me who just like to do this, right? So I sit on the committees of PhD students in different fields. I love learning. I love to see what other people are doing for inspiration, for learning. There are people like me. And SUTD was very strategic to recruit a lot of people like me in the first few years. But at the same time, for some subject, you probably can't find so many people like me, right? Most of the faculty members are trained in traditional engineering domains. When you hire them, it's very challenging because they will generate some resistance to collaborate, but they will still collaborate to write proposals because of money. They need, for junior faculty like assistant professors, they need research funding, right? So they will be pressurized to write proposals to IDC. Can you hear me now? Sorry? Hello? 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 Hello, can you hear me? Hello? Hello, can you hear me? Hello? Okay, so let me continue since you can hear me. So my point is that so SUTD was very strategic to hire people, try the best to hire people like me who are interested in multidisciplinary collaboration for learning and innovation. If you can find so many people like me, and you can use a top-down scheme like IDC and making calls for research grants, but the proposal require collaboration across different peers. And maybe for assistant professors, those are very teaching opportunities. They will try it. Maybe at the beginning, it was very frustrating for them. So they have to find people from other disciplines. They might write proposals with a lot of frustration and challenges, but that's no problem. And by working together, you will find once they enjoy the benefits of collaboration, they will continue to do that. They will continue to do that. So the IDC working principle actually fostered collaboration and allowed the junior faculty from traditional disciplines to learn about the benefits of collaboration across different domains by designing something together. So that changes the mindset and the culture, educates specialized faculty researchers, and to become more multidisciplinary and more open to collaboration and innovation.
Hello.
Yes,
这边可以
yes, I can hear you.
你把这个声音关掉。对 ，Hello。能
Yes.
能听到吗？现在？
可以，可以，
Okay.
又可以了。
We are using now this phone. Okay, we use the computer, and it breaks down again, and now we use this.
Ah, 这个问题，这个早上应该解决了，为什么现在解决了？
可以的，可以的，
你把这个关掉。
Okay,
Professor Law, can you hear me now?
Oh, yes, yes, it works.
Hello. Hello.
可以听到，可以听到。Yes.
他那边没有反应了。Professor Law?
Yes, yes, I can hear you.
Okay. So I don't. Now can you hear me?
Yeah, no problem. It works.
Okay, but okay, I'm just want to make sure that anyone else has any questions or comments. Okay, so Professor Law, actually I have a lot of questions for you, but due to the technical issues, I may save the questions for our later discussions.
Yeah.
Okay.
We'll talk more later, for sure. Yeah.
Okay. So since we're already 22 minutes past our original schedule, so I'd like to thank you, Professor Law, for the great introductions and showing us these new areas. Okay, this is really an area that is missing in China, and we should actually pay attention to these topics. And I really thank Professor Law for bringing in these new concepts and idea to our faculty and students. And we will keep in touch, and we will try to learn more from you, Professor Law. Thank you so much.
Yeah, thank you, Prof. Chan, for this opportunity for me to share my research and my experience, and I certainly look forward to more interactions and sharing. Yeah.
Okay, great, and thank you. Yeah, and thank you everyone for joining us today. So I think that's now conclude our online presentations. And Professor Law, please remain. So Professor Gao and me, and also Professor He here, and Professor Zhang Ke are here, and would like to discuss with you in further details.
Sure.
Okay.
I'll stay on. Yeah.
Bye-bye, everyone. Thank you. Sorry for the technical issues. And also Professor Xu Weiguo 老师, and who else? I think there are some other faculty member.
I'm here.
Okay, Professor Xu, 你稍微再等等好不好？我们先等那个其他的同学先离开，然后我们跟罗老师我们再稍微聊一聊。还有哪位老师也是？秋玲是不是也可以？对，秋玲也稍微等等哈。秋玲还有谁？李曼元是吧？李曼元是我们的 OK， 那不是 ，sorry。好，其他同学可以离开了。 那我们是不是用微信还是继续用这个？
用微信通话就可以。
对，不然的话，这个我担心他待会儿听不清楚。
微信吧，微信也可以。
微信那我们要把徐卫国还有秋玲要加进来。
现在这样能听得见吗？就是现在这样。
可以，现在可以，现在可以听见。
秋玲，你们能听到吗？秋玲还有徐老师。
可以，我可以听到。
我这可以。
哦 ，OK， 好。那其他同学请先离开吧，好吧？宇璇，你们离开。激光，你们
但他们有可能有的人他打开了，他人可能暂时离。
那把他踢掉吧。
对，把他踢一下。对，
他们踢掉。
这会怎么信号好点了没？
那我们用电脑可以。
用电脑。
那我们现在聊一聊吧，就是罗老师的那个。
行，
然后。
问了吗？那个有吗？你的问题问了吗？
还没，这现在问问，刚才这搞不定啊，那个一直就没有。
那你可以现在就开始问起来算了。
罗老师。
我们这个我们何老师，我们的培养处的
那个
处长何
老师，我叫何永红，对，我就是那个，我就是对您那个，就是在做这个 engineer thinking 的时候，你不是做了那个一个工具叫 GPS 啊，对，那个它大概是一个，我理解是不是就是像一个 searching engine 呢？就是那个 search engine， 就是像那个一个搜索引擎一样的。它是因为据我知道，就是像美国有一个公司叫 Yext 啊，就是它也是基于那个知识图谱，就是那个 knowledge graph 去做那个 searching。那么你这边对这些 knowledge 的这 distance 这个模型啊，你是不是也是根据